how's it going? This is a little bonus video for the Unit 2 review. And even though Unit 2 deals with limits and continuity, there may be a problem or two in the review packets that I have that deal with differentiability, derivatives. Now, Unit 3 is where we're going to do the review for derivatives. But since we already have a base for derivatives, I feel this is a good time to show you this so you can answer a problem or two on the review packets. So let's take a look at the problem we're given. We're given a piecewise function f of x, and it equals 2x plus 9, given the condition that x is in between or equal to -6 and -2. And when x is greater than -2 or less than or equal to 3, my f of x equals x squared plus 1, all right? And what I have off here to the left is an actual graph of these two functions. You'll notice that the yellow part, okay, is denoted in yellow on the graph, and the red part here is denoted with the red, okay, line or curve on our graph. And let's answer the following two questions. First of all, this unit deals with continuity, so let's answer this first question here. Is f of x continuous at x equals -2? Okay, so the first thing I want to do is I want to locate where is -2. That is right here, okay? So that means any place my graph approaches -2, because continuity, okay, in order for something to be continuous, the limit at -2 has to actually equal what the value of f of -2 is, okay? So let me write that down, what I just said. So let's call this A and this B here, okay, our second question. So for question A, in order to figure out if it is continuous at -2, the limit as my function, okay, approaches -2 has to equal what f of -2 is in the function, okay? So let's take a look at the limit first. This is very easy when it's done visually, okay? As I approach -2 from my left side and my right side, it should be the same value to have a limit overall. Let me say that one more time. As I approach, we'll use green. From my left side, -2, and I approach it from my right side, it should approach the same y value, and it is 5, okay? So, let's go over that again, shall we? As I approach -2 from the left, it should be the same thing as I approach -2 from the right, and that happens to be a y value of 5. So we're good. So what I'm going to do is I'm going to say that, right, the limit as x approaches -2 of f of x is 5. So now I got to figure out, well, what about f of -2? Is that 5? If it is, and they're the same thing, then it is continuous, okay? So when I pick -2, the million-dollar question is, do I use my top equation? My bottom equation, okay? When x is -2, x does not equal -2 here. X is greater than -2. See this little line underneath here? That tells me when x is -2, I'm going to use this equation. So let's take that and throw -2 into our equation, our linear equation right here, okay? So I'm just referencing this now, okay? 2x plus 9 when x is -2. So it's 2 times -2 plus 9. That's -4 plus 9. That is indeed 5, okay? Since they are the same thing and they're equal, that tells me yes, that proves continuity. Is f of x continuous at x equals -2? Yes. Please answer it. You have proved it with your math work so wonderfully. Now answer the friggin' question. And it is yes. Okay? Okay. All this work here is justification, but this is the answer. Okay, we justified our answer. Please do not forget to answer the question. Now, let's take a look at B. Okay, the second question right here. Is it differentiable? Okay, now I'm going to, I want to erase all this stuff because I want to work right next to my graph as well. So make sure you have this all written down. If you don't, pause this video because I'm about to erase this, all right? Now, derivatives work in the same fashion as continuity. We don't really think about it that way, but it does, okay? Now they're asking you, is f of x differentiable at x equals -2? Which means, is there a derivative at -2? Can I take the derivative at -2? Let us not forget, children, this is our -2. This line right here is -2, right? So where does our function touch -2? Right here, this mountaintop, okay? Right here at this mountaintop, all right? Now, those of us that are familiar with derivatives can tell right away that is not differentiable. How come? You cannot take the derivative of a corner or a cusp. That is not a smooth transition. That is not a line. If I zoom into that, that will always look like a corner. So I know right now that for B, the answer is no, it is not differentiable. But if they ask us to justify that, and that's what the point of this whole video is, okay? Justification for that answer. Derivatives are the same things as limits, meaning in order to find if something is differentiable at x equals -2, that means my derivative as I approach -2 from the left has to equal my derivative, and this notation is not the proper notation. I'm just writing as I'm reading, okay? My derivative of f of x, this is how I should really write it. I am so sorry, but we should write things the right way. The derivative of f of x as x approaches -2 from the left has to equal the derivative of f of x as x approaches -2 from the right side. Okay? Those two derivatives have to be the same. All right, that's justification. We really don't look at that often, but every once in a while it pops up on a final, every once in a while, and it pops up on one or two of the questions for the review for Unit 2. How come? How come it pops up if we're talking about limits and continuity? Because in order to justify the derivative this way, it's the same thing, the same way we do limits and continuity, approaching from the left and right, except instead of continuity, it's the derivative from the left and the derivative from the right. Okay, let's take a look at this now. Let's take a look at the derivative from the left of -2 and the derivative as I'm approaching from the right of -2. First thing is I will do a highlighter, thick one. As I approach -2 from the left, it is coming this way. That is a straight line. I will undo that so we can see our line. Okay? That is a straight line. The derivative of a straight line is a constant, right? It never changes. So what I need to do is take the derivative of this, okay? Because that's the equation coming from the left side. If I did not have a picture of this graph, how would I know which equation is coming from the left side and the right side? The x values are smaller than -2 here, aren't they? If they're smaller, aren't they on the left side of -2? They are, okay? So the derivative from the left side means I need to take the derivative of 2x plus 9, and that ends up being 2. The derivative is 2. That means this line just has a slope of 2. That makes sense. It's a straight line. The slope never changes. Let's take a look at the derivative from the right side. Okay? I want to take the derivative from the right side of -2. But mister, this does not include -2. That's okay. It's as it's approaching -2. Okay? How do I know this is the right side? Because these x values are all bigger than -2, aren't they? If the values are bigger than negative 2, then on my number line, they are to the right of negative 2, aren't they? Okay? So I want to take the derivative of my right side, which is x squared plus 1. Okay? Let's do some math over here to the side. Okay, the derivative of this right here now is 2x at x equals negative 2, let's not forget. Well, Visca, how come we didn't have to plug in x equals negative 2 here? Because there's no x anymore. It's a constant. There's no x to plug in x equals negative 2. Here, we do have an x value, so it's 2 times negative 2, which is negative 4. So my slope from the right side is negative 4. These are not equal, okay? What it's telling me is this slope, as I get closer and closer to 2 from the right side, is approaching a slope of negative 4. Okay? If I have a slope of positive 2, okay, and it's connecting a slope of negative 4, which is a little bit steeper, that will form, oh wow, weird, that will form a corner or a cusp. That is how we can tell it is not differentiable. That is how we can tell there is no derivative there. So my answer is no. This is my justification. All I did, I'm going to make this real easy. I was explaining things as we went in which you needed to hear to understand. I took the derivative of the left side, and I took the derivative of the right side. If they're equal, well, then that's what the derivative is. If they're not equal, it's going to form a cusp or a corner or some discontinuous something, and then it doesn't have a derivative, like our problem here for B. So that's it. We're good. In a better situation, let's say I took the derivative of the left side and it ended up being 3. I'm making this up, right? And the derivative from the right side ended up being 3. Then the derivative, it would be differentiable. The derivative would be 3. So if here's my point where they're meeting, and it had a slope of 3 from the left, and it has a slope of 3 from the right, well then yeah, look at, that's a straight line. That's a derivative, straight through, 3. In our case, it does not have that. So we are good to go with an answer of no. See ya. Have fun with those practice problems.
Say.